I'm super honored to accept this Lehigh Hintze Award. I'm humbled. It's pretty amazing to think that my name is on that plaque now with some really truly great geologists. And I want to thank Bill Lund and Pete Rowley for their nomination and others who wrote letters of support. And thank the nominating committee itself just for this very difficult task of choosing one person out of a pool of a bunch of qualified candidates. So I'm grateful for that. And if I've done anything really to deserve this award, it's really for two main reasons. And one of them is my wife, Lisa Graves, over here. Lisa's an artist. She's not that deeply into rocks and geology, but she has made it possible for me to be crazy interested in rocks and geology. So thank you. And the other reason, I mean, I wouldn't have done any of this if I didn't have a great manager. And Grant has given me unstinting support over the years. He shielded me from all of the difficult business of running a successful mapping program. And he gave me the opportunity, the really rare opportunity to go out there and map, to hike in Utah's mountains and valleys and urban fringe areas and look at rocks and geology and make geologic maps. And that was amazing. The freedom that he gave me to do that and the trust that he showed in doing that, really combined with the incredible support staff we have here at UGS and the scientific staff, that's what made this possible. And I'd do it again in a heartbeat if my knees would let me, you know. So yeah, I mean, thank you for this award. It's amazing. But as part of that, I'm going to tell you some stories about this Markagunt gravity slide complex. And this is not about me. This, see how to work this here. There are a lot of people that have been working on this discovery. And I've worked closely the last 10 years with Pete Rowley and David Hacker on fleshing out our understanding of what these big, gigantic, what I like to call mega landslides actually are. And in the past 4 years, we've worked really closely with what I like to call our NSF crew. And that includes David Hacker, but also Ashley Griffith. He's a geomechanics, rock mechanics specialist, with Dave Malone, who's big into detrital zircon geochronology, and Tiffany Rivera, who's now at the University of Missouri, a volcanologist and geochronologist. So working with them and their students, over a dozen master's and PhD students in the past 4 years have been working on these slides. That's not all. There are others that are working independently on these slide rocks or on the foundational sediments at the slides restaurant, and that includes Jeff Eaton, Brian Hika, a geochronologist at University of Wisconsin, Eric Farah, paleomag specialist, and Harry Philcorn, who's one of the early mappers out in the mid-1980s up on the high plateaus above Cedar City. So a lot of people have been involved in this, and that's amazing. All of this is happening just within the past 10 years and past 4 years. So what I want to try to do today, got two main goals. One, I know there's a lot of people here that don't know a lot about these slides and that are listening online. So just give a very brief summary of what are Utah's gigantic mega landslides. And it's hard for me to know what to talk about on these because the rocks are so amazing, the size is so amazing, the mechanics about how these things moved is so amazing. So what do I focus on? I mean, the history of their discovery, I think, is fascinating that's just a beautiful story about how science actually works. And I'm going to tell you where you can read about that stuff. But today I want to talk about some of this newer research that people are doing. So let's jump right into it. And this is Lehi's Hintze's original geologic map of Utah. And what we're going to look at is this area in pink, the Marysvale volcanic field. That field was active from about 30 to 14 million years ago. It's the heart of the Tushar Mountains now. It's this deeply eroded volcanoes and calderas. And this is all pre-basin range extension. So Western Utah looked very different at the time. Nevada looked very different. That was all part of a high elevation plateau that people call the Great Basin Altiplano. It was studded with volcanic mountains and calderas. And some of those calderas on the present day Utah-Nevada border erupted big ash flow tuffs that made it all the way into the Marysvale field, 80 miles or more to the east. So big eruptions. And those are important in this story because they're really cool rocks. They're easily recognizable in this volcanic field that is otherwise a lot of gray and brown volcanic rocks that are hard to tell apart. So they're good markers. They erupted essentially instantaneously. They blanketed the landscape, and so they preserve a record of what that landscape and what the structures looked like back when they were erupted. And so they, see where I want to go with this here. In essence, they're important markers in that volcanic field. So they allow us to kind of tease out not only the effects of this modern basin range extension, but this earlier episode of southward gravitational collapse of that Marysvale volcanic field. That volcanic field, I should mention too, is built on a very weak substrate of up to several hundred meters of these fine-grained, clay-rich volcaniclastic sediments. It's just a very weak foundation for all these volcanoes to have grown on. And today, this area is part of a transition zone between the modern basin and range in the heart of the Colorado Plateau. And that's fortuitous for us because it means that volcanic field is cut by big, large displacement, high angle normal faults. And so we get a peek right down into the guts of the volcanoes and actually down into the base of the slides that we wouldn't otherwise not be able to see. Let's see. So what are these slides? Well, I'd like you to think of them as these thick, southward tapering wedges of volcanic rocks. They're about a mile thick in the heart of the field, and they failed catastrophically southward and tapering to a few hundred feet at their southern end. And this is the first one of these of three gigantic slides. This arrow represents the Sevier gravity slide, named after the Sevier Plateau there just north of Bryce Canyon National Park. We've got the Markagunt gravity slide shown in green, and then finally the Black Mountains gravity slide shown in blue here. We can show that each of these moved over the former land surface at least 20 miles, 30 kilometers. And we have good evidence that they did that very rapidly. Each of those was preceded by slow gravitational spreading of this volcanic field, because those volcanoes, I mean, the Earth's crust can't support such massive piles of rock. That slowly spreads to a broader, more stable profile. And it did that along this black feature we call the Markagunt thrust fault system. And that's a widely recognized process at volcanoes worldwide today. They just slowly spread out to more stable profiles. And that's what happened here. The types of deformation that we see on these slides is really variable from north to south, and there's a good reason for that. And the reason is that each of these is is essentially a very large landslide. And like, this is just a block diagram, a kind of cartoon of the Markagunt gravity slide. And it's 60 miles from the head to the toe, so these are big. But think of this as just a small little landslide up here in the foothills. It's exactly the same thing. Like a modern slide, it displays different styles of deformation depending where you are on that slide. At the breakaway area, you see extensional deformation. You see normal faults that drop blocks down against one another. On what we call this bedding plane slip surface, we see simple translational movement. At the ramp, we see extreme kind of compressional deformation and thrust faulting. And that's where this slide mass actually ramped up onto the former land surface. And so over the former land surface, then we see older on younger rock relationships. We see thinning of strata as it spreads out on the former land surface. We see rotated and back tilted blocks and strike slip faulting and all sorts of great things. And then finally, at the very end of the landslide, we have what we call these debris avalanche deposits, where the slide just is completely broken apart into chaotic blocks. And we see this stuff on each of these slides. That was actually really confusing to people early on. The first people up that were mapping up high in this country in the Marysvales and on these high plateaus saw all of this different style of deformation. Normal faulting, thrust faulting, strike slip faulting, oblique slip faulting, all in a pretty small area. And they were thinking tectonically, how can you have that variety of tectonic deformation in such a small area? You can't. And we don't have it here. We have landslides here. And you do see that in landslides at any scale. You know, the size of this room, you're going to see those sorts of structures. This just happens to be big. And it's really big. If we were to superimpose the outline of these slides on the modern day Wasatch Front, I mean, this is kind of roughly what it looks like. It stretches from southern Ogden to Provo. I mean, this still blows my mind. From western Tooele Valley over to the impinging on the Uinta Mountains. It covers about 8,000 square kilometers, 3,000 square miles, about the size of Yellowstone National Park. The volume of all that slide debris would fill the Grand Canyon nearly to the rim. So these are big. They were completely unknown 10 years ago, right here. So I think that's pretty cool. That's sort of what we know now. Very brief introduction to these slides. I want to backtrack a bit, back to 2015, when we published what is shown in the black outline here. That's a Panguitch 30 by 60 quad. It's about 1,700 square miles between Cedar City and Bryce Canyon. Grant gave me 4 years to make this map. 400 square miles a year. So we were doing fast reconnaissance scale mapping. We're trying to get the big picture together so we could go back later and map select areas in more detail. And this is kind of what we knew in 2015. We knew we had something we called the Markagunt gravity slide. We didn't know the full extent of it. Embarrassed to say, we didn't even know the Sevier gravity slide existed. There's no yellow arrow on that map there. We didn't know the Black Mountains gravity slide existed, but we did what Pete Rowley has always told me to do. We publish, we publish, we publish. You know, we work for the taxpayers and we publish our discoveries as we make them. And so that's what we did. But in 2015, we knew enough to know that we didn't know enough. We needed help to understand these things. It was, I mean, that's way over my pay grade. But what we did know is that shown with this little pink star is something called the Markagunt megabreccia. And that's something that these early workers had discovered in the 1980s and published on in 1993 before all of that work came to a stop. But they found up on the plateau above Cedar City a chaotic mix of old volcanic rocks sitting on top of young volcanic rocks. There was nowhere for it to have come from. This is up at 11,000 feet. And it just, the poor students that were sent out there to map is like, I feel for them. They didn't know what to make of it. But we knew that our idea of the Markagunt gravity slide was so much bigger than what they had been able to find back in the day. And so what we did is convene a 6-day field forum. It was sponsored by the Geological Society of America, by UGA and others. And we brought together nearly 30 people with backgrounds in rock mechanics and structure and landsliding and geochronology and all these different specialties to spend a week in the field looking at rocks. And it was amazing. 2 important things came of this meeting. One is a field guide that we published in, forget the date, 2019, I think. But it describes these slides, the kind of deformation we see, the history of their discovery, which is, I think, a really interesting story. But importantly, it lists several dozen localities where you can go and see this stuff. We kicked out a version of that guide for general audiences a couple years later. That's available here in the DNR bookstore. You can pick that up in the Parks book at the same time. But what it also did is that several of those people that were on this week-long field forum got together, submitted a proposal to the National Science Foundation and got it funded to look at these slides in more detail, to look at the mechanics and the mobility mechanisms that allowed them to move 20 miles over the former land surface and to just better understand their age and their extent. And so that's, I think, let's talk now about some of that new research that is going on. And this is Haycock Mountain. It's my favorite place in the whole state, despite all the beautiful red rock country, despite mapping in Zion and Bryce and Cedar Breaks. This piddly little hill is amazing. What it shows and why I went here, it was interpreted before as a normal section of rocks. And I was just starting out to map. And so you gotta walk a lot of sections. You gotta be able to recognize these things where you're mapping in areas where they're not well exposed or where they're faulted and concealed. And so this was a good section. The white and gray are these Brian Head Formation rocks. This is the weak substrate up there that this field is built on. On top of it is one of these big regional ash flow tuffs, the Isom Formation. So a normal section here, so I went to study it. I get up to the base of the Isom, and I didn't see what I expected to see. This is what I saw. And there's 2 important points here. One is that ash flow tuff has been crushed to gravel and sand sized pieces, and that deformation decreases up section. So if you were to stand on top of Haycock Mountain, that ash flow tuff just looks fine. And that's what people did in the past. But the base tells a different story. The other part of this is the base of the Isom. Look at that very flat surface. We don't see a vitrophere here at the base of this ash flow tuff like we like to see, this black, glassy, chilled zone. We see this incredibly sharp contact, below which lies what we call a basal breccia, or basal layer. And that very flat surface is grooved and striated and fractured so that we can say that those upper plate rocks actually moved from the north to the south. And the basal breccia consists of ground up upper and lower plate rocks of the brine head and the isom that behaved as an overpressured fluid at the base of the slide, helped to reduce the effective friction on the slide and facilitated movement of the slide. And so we found exposure, I found exposures like this all over Haycock Mountain, wherever we see the base see that contact. And what that told me is that this Haycock Mountain, it's 6 miles long, that it's not a normal section, it's not in place, it's actually part of what people were calling this Markagunt mega breccia. And so that mega breccia then had to be a lot bigger than people had thought. Some of the early work that this NSF crew did was right here at Haycock Mountain. And this is Dave Malone in the green jacket. That's Jeff Keith. They're looking at the basal breccia in that slide plane. But Dave and his students analyzed detrital zircons out of this basal layer and enclosing rocks. And zircons are these really tough, resistant crystals found in a lot of volcanic rocks and in the sediments derived from those rocks. And they contain trace amounts of uranium in their crystal structure. So you can date these crystals. And that's what Dave specializes in. So he dated these layers. And what he found is that basal layer is actually 23 million years old, cannot be older than 23 million years old. And so we don't have a normal section here. We knew that, but this is another way to prove that. We have an older on younger rock relationship. That isom formation is 27 million years old. It sits on something that's 23, which sits on the underlying brine head, which here is about 34. So we do have these older on younger relationships at Haycock Mountain, and that's what we see at the toe of the landslides. I'm missing something here. I'm going to go on to the next one. Another important site for us here, and here's what we're looking at are these darker brown volcanic mudflow deposits sitting on these lighter gray volcaniclastic sandstones, and that's a normal section here. That contact is actually often very sharp like this, easy to map. Here, though, it's not a contact. If you walk up to it, you see that it is a shear plane, and it's lined with obsidian-like glass. And that glass has been injected as dikes into these lower plate rocks. If you look on top of that shear plane, you can see bubbles, vesicles, and flow features and fractures that tell you that upper plate moved from the north to the south. Most of that glass looks like jet black obsidian. I mean, it's beautiful, beautiful glass. If you look at it in thin section under crossed polars, this is what it looks like. It's isotropic, it's black, that's what glass is. You see a few partly melted phenocrysts there, quartz grains. Uncross those polars, and it's a beautiful glass. You see some vesicles, you see flow features. We had Barb Nash at the University of Utah, since retired, but she analyzed this glass and told us it is actually of basaltic composition. A basaltic glass, a volcanic basaltic glass, is something they call tachyllite. But this isn't volcanic, it's a friction-generated melt, and so they tack on the name pseudo. So it's a pseudo-tachyllite. And it's a rare rock type that is normally associated with fault zones having formed at great depth in Earth's crust or on large impact events. But this is the first recorded occurrence of pseudotachyllite generated by landsliding known in North America. It's one of the few examples in the world, actually. And it's one of, I would bet, the best example in the world. We've found pseudotachyllite now at more than a dozen sites and in some layers, insanely thick amounts of glass. If you could date this glass, you'd date the slide, right? Because this formed from friction generated during slide movement. But glass is really tough to date. And this is a low potassium glass, so it's really, really tough to date. But Tiffany Rivera here on the left, and her student Mickey Holliday with Brian Hika there have dated it, and have got a good age of 23 million years old. They've dated other glass on the Sevier slide, and in combination, this age here of 23 in combination with ages that kind of bracket and placement of the slides, they can tell. Now I have to get my notes because I don't remember the numbers. They were able to use this age in concert with others to bracket the emplacement of the Markagunt gravity slide to, I think 20, let's see. I want to get the number right. It's a new number here. 23.05 MA, plus or minus, what is it, plus or minus? So about 23 MA. Yes, okay. Anyhow, they've done a lot of dating, not just of the pseudotachyllite, but of these other ash flow tuffs that help us pin down the dates of emplacement. Just one more note about this outcrop. This is Eric Farah from University of Louisiana. He's a paleomag specialist. He and his student, she did her thesis at this one outcrop, at this pseudotachyllite outcrop. And what Eric did is he's developed what he calls his mini AMS method to look at the mechanics of frictional melts. And what that means is that Eric can cut out a little tiny pea-sized cube of that glass and analyze it, analyze the magnetic properties of that glass, and tell us how the adjacent rocks were moving at the time the glass formed. And that's pretty cool. And what they found is that the rocks here were moving from the north to the south, with the top to the south central direction, which is what we can tell from field mapping. But this is a wholly independent way to document that. So pretty cool stuff that he and his student did, and they published that back in, I think, in 2021. We'll see the paper in just a bit here. This is a cartoon of the three gravity slides, Black Mountains, Markagunt, and Sevier. And we've been looking on the green at Haycock Mountain and that pseudotachyllite site. But I want to jump over now, just over to the south end of the Sevier Plateau here, and show you a couple things. This is the light gray and white, again, is our Brine Head Formation, the base, greasy base of the slides, and the cliffs up there are Mount Dutton Formation, these distal volcanic mud flows way down far on the flanks of the volcanoes. And that's what people thought in the past, anyhow. Turns out that whole cliff, it's 100 and some feet high, is one of these basal layers. And you can walk up there to the base of the cliff. Big blocks of it have come rolling down. And what you see are these elongated, intensely deformed clasts of ash flow tuffs. If you walk up to the cliffs themselves, You look there, you can see they're kind of shiny in this photograph. They're silicified. They're kind of look stretched out. And on this field form, I called them taffy clasts because it looks like hot taffy, right? So these rock mechanics guys said, no, don't use that word. Because we're not talking about super high pressures and high temperatures deep in the Earth's crust. This is something very shallow. They think it formed through deformation during cataclastic flow of this basal layer. And I don't pretend to understand that, but they're really neat things that we see in this basal layer. All along the southern margin of that Sevier plateau, we find examples of really amazing deformation. These are clastic dikes. Zach Lawford did a lot of mapping of the Sevier plateau here. He's one of David Acker's students. And this is 500 feet above the base of the slide. And we see clastic dikes. They're amazing things. We also see big blocks of the Bryan Head Formation itself thrust up into the base of the slide. Here's a little closer look at it, that big white block. It's a southern end of again, the southern end of the plateau. We see a distributed zone of deformation that includes these kind of southward thrust faults and folds in the Bryan Head Formation itself, and then in those darker overlying rocks, extreme shear deformation, hundreds of feet above the base of the slides. And so this severe gravity slide soon became a focus of new work for this NSF crew. And this is Mike Braunagel, one of Ashley Griffith's students who just, well, a year ago finished his PhD on the Sevier slide. And here he's standing in front of the Kingston Canyon tuff. You see a couple clastic dikes cutting through that and rocks on top that look planar and undisturbed. So Mike mapped deformation he saw at the base of the slide, but he also looked at the mobility mechanisms of how the slides actually moved. He did some modeling. He did a lot of great work on this. This is just one of Mike's illustrations. He showed that where the slide was going over the former land surface and hit a bump, hit a hill or something, it just peeled off sheets from the lower plate and stacked them up like some thrust duplexes, and eventually overrode that and continued going. And the interesting thing here that Mike has shown is above all this deformation here, look above. Everything is kind of hunky-dory, looks planar, undeformed. Here's another view of that. Extreme deformation below that little black band right here is the Kingston Canyon tuff, and above those volcanic mudflows. I mean, that looks like a great unconformity to me. It's not. Those mudflows have traveled probably 10 miles or so. They're undeformed because of the Kingston Canyon tuff. The Kingston Canyon tuff is helped constrain elevated fluid pressures at the base of these slides. And so deformation is restricted to a very narrow zone at the base of the slide, but where that slide was moving, it had progressively eroded away the Kingston Canyon tuff, and where it's missing, that deformation just blossoms up into both lower plate and upper plate. And here's one example of that. This cliff, I don't know, it's a couple hundred feet high, but just tremendous shear deformation of the upper plate. The Kingston Canyon tuff helped constrain those fluid pressures. Where it was gone, we'd lose fluid pressures, lose those fluid pressures, we increase frictional resistance, we get a increased shearing and deformation throughout the body of the slide until it finally came to a stop. So some pretty cool stuff there. A couple more things. Talk just a bit more about the timing. At the beginning of this NSF project 4 years ago, we kind of knew this, that the Markagunt, that the Sevier slide was about 25 million years old. The Markagunt slide was about 23, and the Black Mountains about 22. But what Tiffany Rivera and Brian Hika and their students have been able to do is date these slides using argon-argon geochronology and Dave Malone with his detrital zircon geochronology. And we have tighter age constraints now in these slides. We've got dozens of new ages that help us tell that story. Just to wrap up here, they've published a kind of a bunch of major papers in the last few years on the pseudotacholites, on the constraining the timing of the emplacement of these slides, and a really interesting study on the concept of tectonic provenance of these basal layers. That paper by Maybach, one of Dave Malone's students, looking at detrital zircons as a way to tell us how these slides have moved and over what materials they've moved. So some really interesting work that is being done. So I'm getting kind of late. I'm just going to wrap up and say that, I mean, these slides are big. Okay, the Markagunt slide alone is it's like 5,000 times bigger than the 1980 Mount St. Helens eruption, you know, volume-wise. Insanely big things. We can show very long transport distances over the former land surface. And one thing I forgot to say, people often ask me, okay, well, how fast did these things go? And in the abstract, there's a typo. I did a lot of cut and paste. I didn't have long to think about this or put that out there, but I said something like 100 meters per second. So how do we know how fast they moved? Okay, the pseudotacholite is key to this because the pseudotacholite, we can tell that temperatures had to be at least 1,200 degrees centigrade. That's like 2,000 degrees Fahrenheit or something, hot enough to melt that rock, okay? You've got to have, I guess what that implies then are high rates of friction to generate the heat to melt that. So how fast is fast? And what the rock mechanics people tell me is their lab studies show that if you had sustained displacement rates of just 1 meter per second, so that, you know, that's kind of a fast little walk, you could generate a friction melt. So that's a lower. But what the modelers tell us with these big landslides is a different story, that speeds of tens of meters per second are probable, and that speeds approaching 100 meters per second are physically possible depending on your model parameters. So let's just play a little game here. We'll travel back in time, early Miocene, when this Markagunt slide happened. You're traveling, let's just say this, we pick a number, it's 30 meters per second. Just as a ballpark, see what that really means. Well, if you were driving down I-15, 80 miles an hour, back in the early Miocene, you might have just barely outrun that slide. At 100 meters per second, 200 miles per hour, no, forget it. I mean, we think they're fast. We can't prove how fast yet, but we know they didn't creep slowly, because you've got to generate that glass. And the only way to do that, I think, is through pretty fast movement. Anyhow, just to wrap up, these are new discoveries And to me, it begs the question of, I mean, they're virtually unique. There's one other slide known in the world that's of comparable size, and that's Heart Mountain in northwestern Wyoming. So we have 4 big slides. They're all in the western US. Are there others elsewhere? I don't know. I mean, I would not be surprised that they just have yet to be discovered, because they're insanely big things. To me, that's really interesting. It's maybe one of the most important aspects of this discovery is that it opens the door to reconsider what we think we know about volcanic terrains in the western US and elsewhere in the world. Gives us kind of permission to think bigger, maybe. And the other important thing is these 3 slides are right in your backyard. All right. There's millions of people that drive over these every year on their way to Bryce Canyon or Zion, and they haven't a clue. And, you know, think about it. What an opportunity to tell this story through road signs or apps or brochures or other things. Something I think kind of that the UGS actually should take a lead on. I mean, you certainly need someone better than me than explaining this stuff to the general public, but I think it's a huge opportunity to tell this story. Now that NSF research is wrapping up, I think, yeah, now's the time to start thinking about that. Anyhow, yeah, happy to take questions. I'm super happy to be here for the reason I'm here. And anyhow, thank you. Yeah.
Yeah, if you have any questions, we don't have any time, but if you want to have any questions here. Bob, that was great. I'm wondering, when you first started making these discoveries, what was the best analog site in the world where something similar has happened?
It's a good question. Something similar would be Heart Mountain. This is northwestern Wyoming. That big, complicated landslide is something that actually Dave Malone, one of our colleagues here, has done a lot of work on, along with many other people. That's been known for 100 years. There's different interpretations out there on it. Is it a superficial landslide? Is it a tectonic thing? Most people are convinced it's a gigantic landslide, as are these. And so that's the only analog we really have for these. I did go up there to look at some of those sites, and that was amazing. The other analogs are just modern day volcanoes, the Cascade volcanoes, for example. Many of those, if you look at them just in Google Earth, you see these big scars on their sides, and you see this rubble field down at the bottom. Those are collapsed volcanoes. They're sector collapses. They're pretty small in the grand scheme of things, but you see many of the same types of deformation in those as we do see here. So. Mm-hmm.
Thank you. I know we're past time. If you guys do want to leave, go ahead. But if you want to keep asking questions, you can also go ahead and do that.
Yeah, happy to answer any questions.
Here, Eugene.
And I can repeat questions if you like. But.
Thanks, Bob. So looking at some of the geochron dates you have on deformation of the basal layer, it helps, I do a lot of work in sort of Western Iron County, and I'm looking at some of those ages really do match emplacement ages of some large monzonite bodies in that area. So when it comes to causal mechanisms here, do you think that it's something to do with some sort of crustal conditioning as well, or is it just purely gravity slides from sort of over leveraged volcanoes?
Thank you for that question. That's something I forgot to actually talk about. On the Sevier slide, Mike Bronigal, who just finished his PhD, looked into that. And what we think is going on is that there is inflation at the heart of the volcanic field, with these magmas being injected into the shallow crust and feeding the volcanoes. And that ultimately is destabilizing the volcanoes. And so on the severe gravity slide especially, we can show now that 25.01 million years ago, within an error of like 50 or 60,000 years, so an incredibly tight window, that slide happened. There was an eruption of an ash flow tuff called the antimony tuff that is dated at like 25.2 or something. Essentially, what the geochronology is telling us is that slide happened, and that led to decompression, melting of magmas and eruption of this antimony tuff, all within this window of at most 50,000 years, but very likely, basically, slide happened, boom. And it can say that because the slide happened and we have this undeformed ash flow tuff sitting on top of it. We don't have any erosional debris of the slide below that. We do see that on the Markagunt slide. We see the slide happen, there was a period of erosion, then we have an ash flow tuff that brackets the age. We don't see that on the severe ones. We think actually the slide happened, it popped the cork, and that the eruption happened. So that one's pretty well constrained. Markagunt, a little less slow. Black Mountains, we don't really have a clue yet as to what's going on, or at least I don't.
Thank you.
Yeah. Other questions? Tom?
Far reaches of my aging brain is isn't the Traverse Range, the south end of the valley, thought to be a smaller version of what you're seeing?
Tom's question is about the Traverse Range here, separating Salt Lake, Utah valleys. Yes, Jeff Keith and his students and colleagues, and Colin is here. He could probably talk more about that. But there are papers out suggesting that the Traverse Mountain block itself is one of these large landslides that came off the ancestral Wasatch Front and is now basically, is it floating in basin fill, or is it, I mean, it is basically, the thought is, yeah, that might be another one. I don't know, but people are working on that. They're putting their ideas out there, and that's how this all works. I mean, people are going to look at that and they'll do some more research, and yeah. We know there's big range front landslides throughout the Great Basin. Some of them are petroleum producing areas. I forget the name of the Railroad Valley in Nevada. But yeah, big landslides happen. These are just maybe a couple orders of magnitude bigger than these others. Yeah.
Thank you.
So Keely, maybe we'll end with a couple of comments here online. First, there's a group down in St. George that's meeting and watching this meeting. They said that they have a good crowd there, including fellow mapper Janice Hayden. So
yes,
they're checking in, saying hello.
Hi, Janice.
And then we'll end with this question. Are there any key features that might indicate the presence of one of these unrecognized mega gravity slides? That question's from Roy Adams. I guess he's asking for telltale signs if they're wandering around the field. What would make them stop in their tracks?
Right. Yeah. Thanks, Roy, for that. Roy is living in Lima, Peru right now. His wife is at the State Department there. He's traveled around a bit around the Peruvian Altiplano and seen volcanoes and, of course, wondering. Peru is actually perhaps an analog for these. It's this high elevation plateau studded with big volcanic mountains and calderas. But yeah, what are the few key things that we look at? And I think for me, the biggest ones are these basal layers and these clastic dikes, these evidence of overpressured fluids that you see at the base of any landslide. And those are different from the types of deformation we see on, for example, normal fault zones or thrust fault zones. And the other key thing, just escaped my head. So those clastic dikes, the basal layers, the evidence for the overpressured fluids. It's funny, I had it at the tip of my tongue. It's one of the things about getting old. Yeah. So the other key thing for us in people that tend to think tectonically, well, could these just be big detachment faults or that sort of thing? We can prove that these, I don't even like to use the word fault. We use the word slip surface. They're not deeply rooted into the Earth's crust. The ramp is the key. That's where it ramps up onto the former land surface, where that fault daylights. And so that's a key thing. And we're only able to see that because we're in that transition zone. It's been ripped apart by big normal faults. And so we can see deep into the heart of the volcanic field and to the base of the slide. So the ramp is key. The evidence for overpressured fluids is key. And then just the whole geometry of things, the different styles of deformation in a relatively small area. Yeah.
Wonderful. That was a good question to end on. Thank you very much. Can we all give Bob, our winner, another round of applause? And thank you. Now that you've given your talk, you've actually earned your plaque. So
Thank you.
congratulations again. And
Thank you, everyone.
thank you all for coming.